Okay, so let's talk about the rational zeros theorem. Recall that rational numbers look like an integer over an integer. So this could be 1/3, -2/5, 5, 0. Those are all rational numbers. So let's suppose we have a polynomial where each coefficient is an integer. So we have integer coefficients. If P over Q in lowest terms is a rational zero of f, then P has to be a factor of the constant, and Q has to be a factor of the leading coefficient. So another way of saying this is, if there are any rational zeros, they have to be of the form a factor of a sub 0, the constant, over a factor of a sub n, the leading coefficient. And again, this is a theorem, so it can be proved, but we don't do a lot of proofs in Math 12. You'll see a lot more proofs in calculus. Okay, so let's look at the next examples, and we'll do the first one on the movie here and the second one in class. So this says just list the potential rational zeros of the polynomial function. Don't attempt to find the zeros. So let's look at factors of a sub 0, which means factors of 2 in this case. So you get plus or minus 1 and plus or minus 2, because positive 1 times positive 2 equals 2, and negative 1 times negative 2 equals 2. Okay, so then we have factors of a sub n, which is the leading coefficient, so that's factors of 6. So you have 1 times 6 and 2, sorry, let me, plus or minus 2 and plus or minus 3. Because 1 times 6 and 2 times 3 are the only pairs of factors for 6. So now we need to do all the possible combinations of plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2, plus or minus 1 over plus or minus 3, plus or minus 1 over plus or minus 6. So that's with this numerator and each of these denominators. And then we have plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 2, and you can see that we're going to get some duplicates. Plus or minus 2 over plus or minus 3, and plus or minus 2 over plus or minus 6. So let's make a unique list, though. We get 1 and negative 1, 1/2 and negative 1/2, 1/3 and negative 1/3, 1/6 and negative 1/6, 2 and negative 2, but then do you see that we already have 1 and negative 1, so that's a duplicate. But then we get 2/3 and negative 2/3, but then we see that 2 over 6 is 1/3, so that's duplicates. So these are all the possible rational zeros. So please say this sentence to yourself. If this polynomial has rational zeros, they will be on this list. This is a 2, sorry. In other words, this is a complete list. There aren't any rational zeros that aren't on this list. So make sure that's very clear to you. If you check every single one of these and none of them work, then the polynomial does not have any rational zeros. Okay? It's a very strong list. So the steps for finding the real zeros of a polynomial function, we're going to use the degree of the polynomial to determine the maximum number of zeros, so we'll know when we should stop, that we found them all. if the polynomial has integer coefficients, use the rational zeros theorem to identify the rational numbers that could possibly be zeros. Then either use substitution, synthetic division, or long division, I think synthetic division is the fastest, to test each of those potential rational zeros. And it works out really well if you get a group of people and you say, okay, you try 1, and you try -1, and you try 2, and you try -2, and you can share the work and then pool your results. So each time a zero, and therefore a factor, is found, then you repeat step 2 on the depressed equation. And I showed you that earlier, but I'll show you again. After you finish synthetic division, you can see what the other factor looks like, which is called the depressed equation. And when you're attempting to find the zeros, remember to use the factoring techniques that you already know. Factor out any greatest common factors, remember factor by grouping, difference of squares, sum and difference of cubes, etc. You need to still remember all that good stuff. Okay, so this first example, we're going to use the rational zeros theorem to find all the real zeros. It doesn't say just find a list, it says find all of them. So factors of -20 are going to be plus or minus 1, plus or minus 20, plus or minus 2, and plus or minus 10, and plus or minus 4, and plus or minus 5, right? 1 and 20, 2 and 10, 4 and 5. Those are the only pairs of factors for 20. And they're all over plus or minus 1 because the leading coefficient is 1. So this is a list of the possible rational zeros. So what we're going to do is synthetic division. Here's the coefficients of my function, and I'm going to try 1 first. I should do this systematically. 9, 9, 20, 20, 0. Voila! Maybe I picked it because of that. So now what I know is x minus 1 is a factor of f of x, and the other factor is x squared plus 9x plus 20, and then you should at least check and see if that factors more, and it looks like it does. So f of x equals x minus 1 times x squared plus 9x plus 20, but that factors more to x plus 5, x plus 4. So we were asked to find all the real zeros. So when x minus 1 equals 0, when x plus 5 equals 0, or when x plus 4 equals 0, each of those will give us 0. So when x equals 1, -5, and -4, this is the list of zeros. And the instructions also say use the zeros to factor f over the real numbers. And I've done that right here. So I factored f. Okay, and we'll do the second example together in class. So the last objective, we're going to talk a little bit about irreducible quadratics. So an irreducible quadratic polynomial can't be factored over the real numbers. So these are things like x squared plus 4. It's prime if you ask to factor only over the real numbers. And anything like this, x squared plus 1, those aren't factorable over the real numbers. So every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible prime quadratic factors. So that means if you have a cubic factor, it has to be able to factor more. So you always can get down to linear and quadratic factors. And let's think about why this would be true. A polynomial function of odd degree that has real coefficients has at least one real zero, because remember the complex zeros come in conjugate pairs. So every odd number can be written as 2k plus 1, where k is an integer. And so if these are the pairs of complex conjugate roots, there's always going to be one left over. So if your polynomial has an odd degree, has at least one real zero. So that's why we can always get down to linear and irreducible quadratics, because if it's degree 3, it has one real zero. Okay, so the next example, notice what's different is this says solve, and it has an equal 0 on it. And come back and look at these examples. They don't have an equal 0 and they don't say solve. So make sure you're very clear on the difference in those instruction sets, and we'll do this one together in class.